In the last video, I told you about different types of congestion, the different timescales that it can occur at, and what some of the consequences might be. We then looked a little bit at the characteristics of congestion control algorithms that we might like to try and design. So we said that we wanted high throughput, we wanted them to be fair amongst the flows competing for the bottleneck links, we wanted the control of congestion to be distributed so that it can scale. In this video, we're going to start looking at basic approaches to controlling congestion. We're going to consider whether the congestion control should take place in the network with specific support at the routers, or whether it should be done at the end hosts. And then I'm going to tell you a little bit about how TCP does it. We're going to start with the basic mechanism called AIMD, or Additive Increase, Multiplicative Decrease. And we're going to study how that works over the next couple of videos before we look in more detail at how TCP congestion control really works in practice. So I'm going to start with a consideration of where to put congestion control. In fact, you may have already been wondering why it is that we can't simply use fair queuing. Notice that we've already seen a way to give everyone a fair share of the outgoing link by simply decomposing the output buffer into per flow queues, as are shown here, so that if I've got multiple flows going through the network, then each flow would be placed into its own queue, and then we use a fair queuing scheduler to divide up that egress rate, let's say R, amongst all of the flows that are contending for it. And so if they're all wanting to send at rate greater than R over 2, then they would each receive R over 2, because that's what a fair queuing scheduler would do. And in fact, this will give us not only a fair behavior, it will actually give us the max min fair at every link across the flows. It'll give us good throughput. Whenever there is work to be done, it will always keep the outgoing line busy. We say it's work conserving, so it'll give good throughput on each of the links. So what's wrong with this basic mechanism? Well, the first thing is that it isn't responsive. It's simply going to divide up the links. But there's nothing here that will tell the sources the rate at which they should send, or give them any indication of how many packets they should send. In fact, if they do send, so if these are each trying to send at the full blast rate, so if there are packets coming in from all directions trying to use these links, then packets will simply be dropped onto the floor as the buffers overflow, and we'll end up wasting a lot of the upstream bandwidth delivering packets over links that eventually get dropped downstream. So we need a way of signaling back to the sources to say, give them some indication of the rate at which they should send or the number of outstanding packets that they can have in the network. So in network-based congestion control, there is explicit feedback that comes from the routers to indicate congestion in the network. So for example, if I have a source A and a destination B, and then some routers in between with some links like this, let's imagine that there are some flows in the network that are coming in from different directions going through this router, causing some congestion to take place right here. One thing that we can do is, if there is congestion, is to try and signal back to A some signal to say there is congestion in the network. You need to reduce the number of packets that you have outstanding or reduce the rate at which you send them. And so the question is, what would we send and how would we get it back to A? We could, for example, say, I'm dropping a packet, or it could be an indication of the occupancy of the buffer, or it could mark that we've just crossed some threshold and so we're getting more congested. Any of these would be examples of congestion. Another one might be that the outgoing link has a certain amount of capacity left over, and as the capacity gets used up, we send a signal back to say how much of that capacity is available. Or it could be a function of all of the signals that I've just mentioned. So the next question is, how do we get that signal back? And how many bits do we use to represent it? So if we're sending back the whole queue occupancy, we'd really like to be able to send a sizable integer value to indicate what the current occupancy is. That would take a lot of bits and it might be complicated. So in practice, generally people look for schemes that use one or a couple of bits to signal back to the source. And then the next question is, how do you get them back to the source? There's no point in creating a whole packet just to send it back to the source if we can piggyback on packets that are already going by. So it's fairly common to use packets, for example, if there's a TCP packet that's coming through, or some kind of two-way communication, to piggyback onto packets going in one direction such that they get sent back in the acknowledgements and eventually get back to the source. There's one particular technique that's called ECN, or Explicit Congestion Notification, in which the routers indicate whether they have some degree of congestion, for example, crossing a threshold. They then mark bits in packets going towards the destination, which then copies those bits back into the acknowledgements going in the other direction. The original scheme that was designed to work somewhat like this was called DECbit. That was proposed more than 20 years ago as a single bit mechanism to signal to the source to slow down. So, nice advantage of a scheme like this is it's simple to understand. We can see that the signal will directly control the behavior of the source. It should be pretty responsive to change because we can detect the onset of congestion in the network and be able to tell the source. It's distributed in the sense that the signal is coming back from all of the routers in the network, and it only affects the source, and so the source can make up its decision, make up its mind on how it will process that signal. And it can be made to be max-min fair. So it can be made to be fair. For example, measure the rate of each flow through the router and pass back the max-min fair allocation for each flow. There are other ways that are simpler, for example, using fair queuing, as I described before. So network-based could certainly work. On the other hand, it's worth asking the question of whether we actually need the network to provide any congestion notification. In other words, can we support congestion control without any support from the network at all, merely by implementing a mechanism at the end hosts where it's just going to simply observe the network behavior. So going to the example that I had before, if I have end hosts A and B and then routers in between, if I'm able to observe behavior of the network such that it's enough to be able to decide at what rate I send or how many outstanding packets I have in the network, then perhaps we can implement a congestion control mechanism this way. This is nice because if it doesn't depend on the behavior of the routers, or it doesn't behave on them sending specific information back, we can evolve and adapt it over time without having to change the network in between. We're going to see that TCP does this. TCP actually does congestion control purely at the end host by observing the network behavior. What it's going to do is, if packets are dropped along the way, it's going to observe this through either a timeout, or it will see a sequence of acknowledgements that are all the same coming back because the data was missing, and so B is going to keep acknowledging an earlier piece of data, which we can interpret as data missing and therefore needing to retransmit it. So if there's been data that's dropped, A could interpret this as congestion and then slow down the rate or have a fewer number of outstanding packets so that it will reduce the congestion in the network. So basically, A is going to observe. It's going to, it's a little bit like it's observing the behavior in the network and seeing what happens in terms of timeouts and duplicate acknowledgements and anything that indicates a drop. It could also see an increase in delay or variance, any of the things that would indicate to it that congestion is occurring so that it can change its behavior accordingly. In TCP's case, it actually has to do this because IP offers no support by default. IP offers no indication of congestion in the network. So when TCP was first conceived, it was actually by necessity that it would control congestion this way. So let me give you a quick introduction to TCP congestion control. TCP implements congestion control at the end host because the network provides no support. It reacts to events observable at the end host. In particular, it's going to use packet loss, or if it believes that there were packets that were dropped. It's going to exploit TCP's sliding window that we use for flow control and retransmissions. It's going to exploit the fact that that's there, and it's going to overload it with a means to control congestion. And I'm going to be explaining that shortly. And the way it's going to do this is it's going to try and figure out how many packets it can safely have outstanding in the network at any time. And this is an important concept. Let me repeat it. It's going to try and figure out how many packets it can safely have outstanding in the network at any time. Now, we're familiar with this already with the sliding window used in TCP, and this is just a reminder of how the sliding window works. Recall that the window is sliding over a stream of bytes, so this is the underlying stream of bytes that we're sending, and that is increasing to the right, so byte 0 was somewhere over here. And the window is telling us data that has been acknowledged. So this is earlier data which has been fully acknowledged. This is outstanding data that has been sent but not yet acknowledged. This is data that's okay to send. In other words, it's data that we perhaps haven't sent yet, but because it's inside the window, we're allowed to send it if we want. And then there is data that is not okay to send yet because it's ahead of the window. The window hasn't slid over the top of this yet because we're still waiting for outstanding acknowledgements over here. Okay, so the sliding window tells us not only which bytes can be outstanding, but also how many bytes. That's the window size. And you will recall that the receiver is going to send back information about what's called the receive window to tell us how many bytes we can have outstanding such that we don't overrun the receiver. And we're going to see in a minute that we're going to reuse that mechanism in a different way at the sender. But just to give a rough idea of what's going on, with the TCP sliding window, here is a view on a timeline of what's taking place when packets are sent and received, and it's going to give us a feeling for how this is going to work. So A is allowed to send up to a window's worth of data and have it outstanding before it receives any acknowledgements. So here is that window of data. And when those packets are sent, of course, each one of them is going to lead to an acknowledgement. So sometime later, we are going to get the acknowledgements, and then we're going to send the next window's worth of data. So if the round trip time is much bigger than the window size, in other words, the time is much bigger than the amount of data that it takes to fill that pipe, then there will be this big delay in between, and TCP will basically move forward by sending a window in a burst, pausing and waiting for acknowledgements, sending a window in a burst, having a pause, and then just repeating like that. So that's in this particular case. Now let's consider a different case, and that is when the round trip time equals the window size. In other words, the window is exactly able to fill up the pipe. The number of outstanding packets that we're allowed to have in the network precisely fills the pipe. In this particular case, the first acknowledgement will come back just after the last packet has been sent, and so we're able to send in a continuous stream. And so there are no pauses, therefore we're using the network more fully than in this case when we've got this idle time. So this gives us a hint as to our ability to keep the network full. Some people would interpret this as a rate because it's the window size divided by the round trip time. And we're going to consider that a little bit later. So that's the basic idea of how this is going to work. More specifically, with TCP congestion control, TCP is going to vary the number of outstanding packets in the network by varying the window size. And it's going to set the window size instead of just being the advertised window, which is what it used before, which came from the receiver to stop overwhelming the receiver. It's also going to take into consideration something called the congestion window. This is something which is calculated at the source. So the advertised window comes from the receiver, and at the source or the transmitter, it's going to calculate the congestion window that's often abbreviated to Seawind. CWND stands for congestion window. And then it will take whichever is the smaller value. In other words, if the network is congested, then it's going to use Seawind, and if the network is not congested, then it will be dominated by the receive window, the one advertised by the receiver. So the next question to ask is, okay, how do we decide the value for Seawind? How are we going to use Seawind in order to change the window size to control congestion in the network? And the scheme that we're going to use is called AIMD. And this is a sort of a classic technique in networking that's used for controlling congestion in a TCP network. And it could be used in any network that uses sliding windows. AIMD stands for Additive Increase and Multiplicative Decrease. Let's start with the additive increase. The way that the window size is going to evolve is as follows, or rather Seawind. If every time a packet is received correctly by the sender, it's going to increase the window size, in fact Seawind, by 1 over W. What this means is that every time a complete window's worth of data has been accepted, has been correctly received and acknowledged, then the sender is going to increase its window size by 1. It'll increase it by 1 over W for every packet. Because there are W packets, then by the end of the window, it will have increased it by 1. So this is the additive increase. It's going to slowly increase when things are going well. If things are going badly and packets are dropped, then it's going to use this as a signal of congestion. And if that happens, it's going to reduce the Seawind by a factor of 2. It's going to halve it. What this will look like is, if we draw the window as a function of time, so this will be the Seawind as a function of time, it's going to start by increasing every time we have a success. And then when we have a drop, so here is the drop taking place here, it's going to drop down to half of its value. So if this is the peak value, then this value down here would be W peak over 2. And then it's going to start increasing again and increasing until it has another drop. And then it's going to increase again and increase again. And it could go up to a higher value because now the network maybe allow more outstanding packets, come down to a different value, and then go up, and then there might be another drop. So it isn't always going to go in this nice, neat, symmetrical sawtooth. This is where the drops are taking place, and it's halving at each case. So here is the additive increase. Here is the multiplicative decrease. The additive increase, the multiplicative decrease. This is often referred to as the Tcp Sawtooth or the AIMD Sawtooth, just because of its shape. If we zoom in, let's take a closer look at what's going on at each step. So let's take a closer look at what's going on here. This is actually proceeding by going in steps. Remember, it's going in steps such that every packet time, it's going to increase by 1 over W. And I'm going to simplify that by saying every RTT, this horizontal dimension is time, it's going to increase by 1. The window sizes are going to increase by 1. Because every time we've acknowledged a complete packet window's worth of data, it's going to increase the window size by 1. So it's going to go forward in these steps of RTT along the horizontal part of the stair, and then it's going to go up by 1, and then RTT, and so on. So this leads to what's often called the AIMD sawtooth or the TCP sawtooth that can look like this. This is an evolution of Seawind, remember that's the congestion window, as a function of time. So here was the additive increase, we had a drop, we dropped down to half the value, we had an additive increase, we dropped down because of a drop that took place, packet drop that took place here. Then we go up again through the additive increase. And you can see here that the available window size, in other words, the amount of data that the source can have outstanding in the network, is varying, presumably because the network conditions are changing. There are other flows in the network, or maybe even the capacity of the links is changing. Maybe they're wireless links, for example. So in summary, we have choice when we're implementing a congestion control algorithm. We can implement it in the network, or we can implement it at the end host. TCP controls congestion from the end host because IP offers it no support by default. So it gives it no signals or indication of congestion other than dropping packets. So it merely reacts to events that are observable at the end host, in particular packet loss. It exploits TCP's sliding window, and that's used for flow control, and it's going to overload that sliding window by changing the window size to try and control congestion. It tries to figure out how many packets it can safely have outstanding in the network at a time, and it's going to vary that window size according to the additive increase, multiplicative decrease algorithm. And we're going to be studying that more in the next 2 videos.